Once you can analyze the structure, you have to evaluate, the actual structure itself or detail it in some fashion. And that gets into selecting the materials that you use. And so there's a variety of materials that we commonly use in construction, but there are also elements that may be beneficial for other reasons, ones that have lower carbon content or other ones that are more durable or other ones that are resistant to damage or other ones yet that would allow us to reduce the congestion or complexity of the details that we use in the structure. So Peer has undertaken a number of studies in the use of high-performance materials, and the next speaker is going to talk about some of those ideas, and there'll be a breakout session also tomorrow to have people who are interested in this area come and talk about possible future activities. I have the great pleasure of introducing Professor Claudia Ostertag from the University of California here at Berkeley. Claudia?
Thank you, Steve. Good afternoon. I hope I will keep you awake. I will do my best. I know it's a little bit late in the afternoon. My talk, as Steve mentioned, will be on high-performance fiber-reinforced composites. And my co-author is Sarah Billington, a professor at Stanford. We have been working in this area with peer funding for the last 2 years. And we specifically looked at two very different high-performance fiber-reinforced composites, which we will describe later on. Briefly, my outline. We look at future challenges, and we see how these future challenges can be met with this high-performance fiber-reinforced composite. And some of you might not be familiar with high-performance fiber-reinforced composites, so I decided to put some characteristics that are very typical of these high-performance fiber-reinforced composites, just to give you an introduction into it. Then we look into some damage resistance of bridge structures with these high-performance composites. And then I will spend some time, because I know when I talk to practitioners, they always look into high-performance fiber-reinforced composite. They have some reservations, they have some questions, they have some concerns, and I thought I will address them with this audience here. And then I will summarize very briefly. Future challenges, as Steve mentioned, it's not only sufficient anymore, so it's important but not sufficient anymore just to look at the safety of a structure, in this case of bridge structures, but you also have to look into the structures that they have to be damage resistant, they have to last longer, and they have to be sustainable. And in sustainable, I mean here that you have to have a lower carbon footprint. And we know about cement, and this has been publicized now quite a bit, about the amount of carbon emissions, 7% globally, that cement industry contributes. But we also have to look at something else, and this is very concerning to us, and this is our resources. For example, something you don't think about, that this is aggregates. We are depleting our aggregates that are non-reactive. Give you an example. Germany is importing its aggregates from Ireland for highway structures because the non-reactive aggregates are completed in Germany. So you are importing this. So what you have to do instead, you really have to be able to work with these reactive aggregates, but make them non-reactive. And so this is one application of these high-performance fiber-reinforced composites as well, which we're actually working with the Federal Highway on that. The problems many of these bridge structures are facing is really deterioration. And you're all familiar with that. I'm just putting here an example up for bridge columns. You are looking into the seismic deterioration, but I'm looking at another one as well, and that's the environmentally induced deterioration. And you have this kind of deterioration even before an earthquake hits. So you can imagine that your structure is not performing as well with your seismic code as you think, because it already has damage beforehand. And one of them is alkali-silica reaction. It's actually called the cancer of concrete. And many structural engineers never thought they would have to work with that. But I know now many of them actually have to learn about the materials issue, about that kind of cancer of concrete, which is alkali-silica reaction. Now, why is it concerning? Because if you look at alkali-silica reaction on the left-hand side, you have all the damage right in the plastic hinge. So you have already a lot of damage, that's why for your seismic performance will not be the same anymore. Now, you're all familiar with this one right here, which is the corrosion. So these kind of environmental damages are very often there before you have an earthquake. The reason why I'm saying that is because I am a member of the Federal Highway Task Force. I'm going around the whole nation. I'm looking at every single state at these kind of damages. And these are pictures I took. It's really sad to see how how our buildings, or not buildings, but our bridge structures are really deteriorating. Next example is bridge approach slabs. And so in this case, it's the same issue. You have a very strong deterioration, and the deterioration is caused by both. Again, it's mechanical loading and it is environmental loading. Mechanical loading just because of the truck loading. You have deflection because of the soil washout, which is a big problem. And you have, of course, fatigue damage, but you also have all the environmental damage associated with it. Here you have all the rebar corrosion, frost action, you have subsidence cracking, you have drying shrinkage cracks, and so on. So it's really, the deterioration is a combination of both environmental and mechanical conditions. Now, what are the effective solutions? What can we do to first meet our challenges and mitigate these kind of problems? And so one solution here would be the use of a high-performance fiber-reinforced composite. Why? Because it provides a higher damage resistance when it's exposed to both loading conditions, so both environmental loading conditions and seismic loading conditions. It also is able to extend the service life and makes more sustainable structure. And on top of it, of course, it enhances the performance of bridge structures as well. First, I want to go into the characteristics of these high-performance composites. What is really so special about them? And so, first of all, if you look here at your flexural performance, what they have is what we call a deflection hardening behavior. A conventional fiber-reinforced composite does not have that, and I'm going a little bit further into that. So this is your deflection hardening behavior right here. I'm giving you an example. This is one of the high-performance fiber-reinforced composites, which is a hybrid fiber-reinforced composite, and I will talk about that one later on. This is tested with, we always test this with large beams, so this is a 6 by 6 by 28 in flexure. Volume fraction is 1.5 volume percent. And what you see here is this is not reinforced. It is just the plain material itself, no reinforcing bars. What you see here, this is your plain concrete, and this is your high-performance fiber-reinforced material. So you have here an increase in ductility, but also an increase in strength. Another example, or another, I should say, characteristics of let me go one step further. I have one other slide, which I think makes it very clear why it's different from a conventional fiber-reinforced composite. If you look here, a conventional fiber-reinforced composite fractures at the same stress level or load level like the concrete. So you have right here, you have some softening behavior right here, but the initiation of the dominant crack is at the same load level. So you can imagine what this does to your durability. It doesn't enhance it at all, because all the aggressive agents can come in as easily as before. Now, in comparison, a high-performance fiber-reinforced, and I have just here the example. In this case here, your dominant crack does not occur here anymore. It is all delayed all the way up to higher strain level. Now you can decide your composite how far you want that dominant crack, at what strain level you want this to occur. In our case, the hybrid fiber reinforced, we designed that dominant crack will occur beyond the yield strain of the steel. So your steel yields at 0.2%. Our hybrid fiber reinforced composites forms the dominant crack at 0.6 to 1% of strain. So you're really delaying that dominant crack to much higher load levels. What is the other characteristics? The other characteristics is in pure tension. So when you do pure tension experiments, you have a tension hardening behavior. And so here you have an example with the ECC. So this is the engineered cementitious composites. So here you can see very clearly what happens to conventional fiber reinforced. You have just purely the softening behavior, whereas for the high-performance fiber reinforced, you see that strain hardening behavior right here. Your dominant crack only occurs at this point right here. This here is all associated with multiple crackings within the material. Now, examples of these high-performance materials that have been used for structural applications. The ECC, most of you are familiar with that. This is a mortar-based matrix, so it has no coarse aggregates. The volume percent is 2 volume percent of PVA fibers. This was developed by Professor Lee at the University of Michigan. And there's another one we looked at, which is the I can't pronounce it, my own material here, hybrid fiber reinforced composite, which is a concrete matrix. So it has coarse aggregates in there. The total volume percent is 1.5. And one thing I want to point out, we specifically wanted to have a concrete matrix. Why? It was so much more difficult to get these kind of characteristics of strain hardening, deflection hardening in a composite with aggregates, with coarse aggregates. But we wanted specifically to do that because we want to avoid the shrinkage and we want to avoid creep. And the best way to do that if you have your coarse aggregates in there. The second thing is, when we developed that, it was not for structural applications. We developed the material for durability. So the durability group is much more familiar with this material than the structural group. So we developed it specifically for durability. That means we wanted to have a crack resistance on multi-scale. We wanted to resist cracking from the micro scale all the way to the macro scale. And therefore, we use different types of fibers in different fiber lengths, different aspect ratios. So it's almost like a gradation of fibers, like you have a gradation of aggregates. So what you have in this case is you have here, sorry, it's a little bit small, but you have here microfibers, and these microfibers bridge the microcracks right at the onset. They delay the propagation of these microcracks into macrocracks. Once you have a macrocrack, then the larger fibers will take over. So what you have here is you have here the 3 different types of fibers that we're using in this hybrid fiber reinforced composite. We use the microfibers, PVA fibers, very small percentage, right here 0.2%, and the rest are steel fibers with different aspect ratios and different strengths. Different lengths, aspect ratio, different lengths. Now we develop what we call 3 generations of these high-performance FRCs right now. So the first one was for bridge approach slab in area 3. People are not familiar with area 3. This is area with very severe environmental conditions. So we looked into that. This was our first generation. The second generation we developed for pier, and this was for self-compacting hybrid fiber reinforced composites for bridge applications, for bridge columns specifically. The third generation we're developing for the Federal Highway right now, where we're actually looking at low carbon footprint. So we're using here cement. The cement is being replaced with very high volume percent with waste material. The aggregates are recycled aggregates that have reactive aggregates in them. So this is a very, very new area, really to look into, really much more sustainable material. But the condition is that they still have to have a strain hardening behavior and deflection hardening behavior as before. Damage resistance in regards to bridge structures, I will have 3 examples here. Example 1 with ECC, and then the other examples were funded by PIER and by Caltrans, specifically in regards to the hybrid fiber reinforced. Example number 1, this was a study that was undertaken by Professor Billington at Stanford, and she looked specifically into the precast segmental bridge piers, and she used the ECC in that hinge region right here. And what you can see here in regards to damage reduction, you have definitely a very large damage reduction at much higher drift ratios compared to your reinforced concrete, the conventional pier. So you really have that evidence of that damage reduction. The other example is with our bridge columns. This is just a view of the lab at Davis Hall itself. And in this case here, we used a self-consolidated hybrid fiber reinforced composite. This was a peer-funded project together with my colleague, Professor Panagiotou. Very briefly, we used 2 different types of designs of bridge columns. One was designed to rock at the column foundation interface, and the other one was designed to form a plastic hinge. So these are larger scale specimens. They're 1 to 4.7 in scale. Aspect ratio is 4, and the axial load we used 10%. I will only talk about the damage resistance, but all this is actually being published now. It's in a peer report. In regards to spalling and damage resistance, what you see here on the left-hand side, what I circled in red, these are our high-performance fiber-reinforced composite columns. So these are the self-consolidated. On the right-hand side, you see the same size of columns, but they contain the conventional concrete. At a similar drift ratio of around 4%, you can see that we have much less damage in the hybrid fiber reinforced composite compared to the control specimen right here. The control specimen here were tested by Tursik Bervesna. And what I want to emphasize here, that this kind of enhancement in damage was obtained despite the fact that we used only half of the transverse reinforcing ratio. So the conventional one has 0.7%, ours has 0.37% as a transverse reinforcing ratio. This is another picture where actually we have the drift ratio of 11% on that specimen, and I'm just, since I was told that I always have to show hysteresis loops, so I have this one right here, where you can see the red one is your self-compacted and the blue one is the conventional one. The next one is an example of a bridge approach slab, and so this is, as I mentioned before, this is area 3, subjected to very severe environmental conditions, and here we wanted to mitigate everything. We really want to mitigate the damage due to mechanical loading, damage due to shrinkage, drying shrinkage, and environmental conditions, corrosion, alkali-silica reaction, frost damage, soil scaling, and so on. So I will show some of these results. In regards to when we tested the half-scale bridge approach slab, this is just the performance here. What you see here, this is your load capacity as a midpoint displacement. This is your reinforced concrete right here. This is your hybrid. It has no reinforcing bars in there. What you see is even the hybrid without reinforcing bars exceeds the stiffness by far of the reinforced. Now, the stiffness is very important for this bridge slabs, because what you feel when you have this soil washout, what do you feel when you go over the bridge? The hump, what everybody hates. And all drivers hate that. This is exactly that deflection right here. So if you are able to make the slab stiffer, what we did with just the hybrid fiber reinforced, it has a very much better quality. This is the reinforced. So we have the same reinforcing ratio like here, which is 0.3%, and you can see the performance enhancement within that kind of composite. Now in regards to cracking. So talking about damage, so here we said, okay, what will happen if we load the specimen, recycle the specimen right here at that load level? And so this is typical a surface load of these bridge approach slabs. So what you see here 3 specimens. I just separate them so you can see them easier. These are 3 specimens of your reinforced concrete. And what you see here is very clearly this very, very dominant cracks. You form very dominant cracks in that specimen. Now let's look into the hybrid fiber reinforced. What you see in this case here, of course, much stiffer, you don't see any cracks. So from a service life point, this is a much better material to be used for these kind of structures. We went one step further. We were just curious what will happen if we double the load. So in this case, we went to 20. So this is the double compared to this one right here. And even at this point, you only have distributed micro-cracking. You don't see this dominant crack right here. Then we pondered that. That's when we did all this environmental test, this corrosion test and so on, because Berkeley is very well, we had this history of that for many, many years, starting with Professor Mehta, looking at durability. So we have all the equipment to look at all these, or do all these measurements for durability studies. So we looked at electrochemical measurements and so on. So we pondered exactly that top surface, that surface that was the tensile surface that was cracked. We pondered that one with a chloride solution to look at corrosion. So I will not go into these electrochemical measurements, but I can mention that the corrosion rate was much lower in the hybrid compared to the control specimen. But what is very visual, of course, is when you look at the rebars. So if you look at the rebars right here, this is your control specimen right here. And this is the dominant crack that you see. You have corrosion along the whole rebar. What we did, we retested the specimen. What you see when you retest it, that the slab fractured at a much lower strain level. So you had premature failure of that slab. Whereas with a hybrid fiber reinforced, you almost have no corrosion damage on the rebar. Frost resistance, this is, I think, very clear. This is your hybrid fiber reinforced after 220 cycles. We follow the ASTM standard in this case. This is your conventional concrete. And there are many, many other tests we performed, but due to time constraint, I will not go into that. You also see that besides the damage enhancement and durability enhancement, you have many other advantages in using these hybrid fiber reinforced composites. One of them is internal confinement and the tension stiffening. I will only mention about a few things that are not on the poster session or poster on the student poster that you can look at in the afternoon, later in the evening. I will just talk a little bit about the confinement. So what you see here, this is the self-consolidated hybrid fiber reinforced we use for the bridge columns. And you can see right here, this is the hybrid fiber reinforced. This is just a control, a self-consolidated concrete, but no fibers. And you can see definitely that difference here, that you have a very stable softening behavior in this hybrid fiber reinforced. And of course, this allows you then to look at damage. And when you see the damage here, you see that you have much less damage. You see here, for example, this is your concrete. You see extensive spalling. This is your stress versus axial displacement at different positions. This is right at the peak load at 7.5 and 12.5. You see very, very large damage in your control specimen. You see much less damage in your self-consolidated hybrid fiber reinforced. And of course, we could validate that with the large-scale verification of the columns. And I just want to point out that this kind of damage resistance was really half the spiral reinforcement. Shear resistance, I will not go into that. This has been really very well known that it provides a very good shear resistance. Professor Willington will talk about that tomorrow afternoon in our material session. Impact resistance, some of you might be interested in that when you come from the nuclear reactor area where you want to have definitely a very good impact resistance. We looked at that one too, and we will have a presentation tomorrow afternoon on that as well. I just want to show you just one graph or one slide of the impact resistance. These are panels. So we looked here at panel size 12 inch by 12 inch by 1, so it's very thin panels. And when you impact them with a projectile, here at 127 meters per second, your concrete specimen really is not only damaged, it fractures in pieces. If you look at the hybrid fiber reinforced, this is what you see. There is no damage, you only have really very fine hairline cracks at a much higher velocity of the projectile. Now, then we come to the reservations. And this is, and now you speaking and I'm answering. So in this case, you might tell me, yes, this is a very nice high-performance fiber-reinforced materials, but they will lead to an initial higher cost. And you're absolutely right. You don't get a higher performance with the same cost. However, what you have to think about is not only the initial cost, and I think we have to go away from that. You have to really think of the whole life cycle. You have to think what are the other advantages that are much more important, that make that material much cheaper actually over the long run. And you should not just look at the initial cost. I know when you have these bids, you always look the lowest one wins, but I think we have to come away from that mentality. Because when you look at these high-performance materials, what they allow you to do is really these very, very new design possibilities because of their higher performance. You can take some of the rebars out, you don't necessarily need them, which will reduce your cost as well. Less repair, that is a very important aspect as well. And I'm coming to that one in a second. However, I just want to point out this section right here, very briefly. What we did with the Carl Sørensen project for bridge approach slabs, we actually proposed here that you don't need these rebars. As you recall, the high FRC performed much better than the 0.3% of the reinforced concrete. So you can either take some of these rebars out, or you can make the section itself thinner, and you save some on the cement. In regards to bridge columns, so far we tested the hybrid fiber reinforced in the whole bridge column. However, Sarah looked at some of the ECC precast just in the hinge section, and we're looking now at some of the hybrid fiber reinforced as permanent formwork. These are structural tubes for permanent formwork. Very durable, very easy to fabricate. The next one is the less repair, and this is a very important one. When you talk to Caltrans, Where really the high cost comes in is not the initial cost, it is the repair cost. It's very expensive for them to bring all the staff out there, to bring all the machine out there, to close the highway lanes, to do the repair work. That is the expensive part. And this is exactly what you can change in regards to the high-performance fiber-reinforced composites. You will have less repair and you have extended service life. And I want to go just back to that one very briefly. This is your damage as a function of time, and this is your initiation of the damage, that's the propagation. And this is your service life right here. What we can do with hybrid fiber reinforced, we can do two things. We can extend the initiation phase, and we can slow down the propagation phase. So your final service life is this one right here, not anymore this one right here. Now, in regards to the initiation, why do you modify the initiation? The initiation is really caused by cracking, and that's exactly what the attributes are of high-performance fiber-reinforced composites. They are very resistant to cracking. So this is why you can delay that kind of damage initiation. And as you recall, I had that picture up before, that you have here a conventional bridge approach slab versus a high-performance fiber-reinforced bridge approach slab. And the cracking here is completely different. Same load level, you have very dominant cracks. That means all the aggressive agents, chlorines, everything can infiltrate your concrete, whereas in this case here, they can't. That means the initiation phase is being enhanced. Now, propagation phase, and this is an important one, and I'm honest about that. I don't know if all hybrid fiber-reinforced composites will have that possibility of enhancing or slowing down that propagation phase. Ours was specifically designed for durability. And this is the reason we were wondering, why does she use microfibers? They are very, very small things. Why does she use microfibers? The microfibers we use specifically for durability issues. Talking about alkali-silica reaction, where does it initiate? It initiates right at the aggregate. That aggregate expands, causes microcracks initially, and we are bridging these microcracks right at the onset. What about corrosion? Corrosion, you have corrosion products right at the rebar. So right here are corrosion products that are expanding, causing these microcracks, and we have the microfibers right there to slow down the cracking of the microcracks. And this is exactly why that kind of propagation phase is being slowed down. Now, the question here I hear very often, for corrosion resistance, why not using stainless steel bar? Perfect, of course. But the issue here is more than that. You have not only in the structural corrosion, you have all the other deterioration processes as well. So you're singling out one, whereas you still have alkali-silica reaction, as you see here, you have all the drying shrinkage cracks and so on. So just focusing on one area is not sufficient. Most of these structures are exposed to many, many of the deterioration processes, not only one. So only targeting one is not sufficient. Next question. Adding fibers reduces workability, makes it very difficult for cast-in-place applications, especially for areas, for structures in seismic-prone regions that are heavily reinforced. Did you ever have that problem? Ever? Did you ever think of that it could be a problem? I hear this very often, and you're absolutely right. Fiber, whenever you add fibers to concrete, your workability goes down. But this is history. Because what you have now is you have now the self-compacting high-performance fiber-reinforced composite. And that's exactly what we used for the bridge approach slab. It was funded, by the bridge column, which was funded by Pier. We used here self-compacting, and if you're not familiar with it, you do the slump test like before, but then you have a pancake afterwards. But you have to make sure that this pancake is very nice and round, because you want to have a very cohesive mix. So you don't have any separation between the matrix, between the paste and the aggregates, and the paste and the fibers. That kind of mix doesn't require any vibration, no internal vibration, no external vibration. It's very, very easy to flow in between these very, very congested areas right here. Next one here, this is a very important one. And to be honest, we were very worried. When Sarah and I did the experiments for Pier, looking at tension stiffening with these kind of materials, we were warned that these kind of high-performance materials really grab onto your rebar. So you have your rebar right here, and I'm doing the same like over Steve. I love this. I always have my fingers explaining things. So you have here your rebar, and the problem was that what the concern was that the matrix will grab onto the rebar and will cause localized deformation. And all your strain hardening will occur right in this localized area. I must say we were very worried about that. Why were we worried about it? Because this is exactly what happens with ultra-high performance fiber-reinforced composites. I'm very familiar with that because a lot of this is being done in Europe with this ultra-high performance. They grab your rebar. We were lucky that in our case, neither ECC nor the hybrid fiber-reinforced, I'm almost finished, fiber-reinforced does that. So what you see in this case here, so these are very large tensile specimens. They're reinforced, the reinforcing ratio 0.2 with a number 5 rebar, and we pull them in tension. And what you see right here, first you see this very nice tension stiffening effect right here. We tested the ECC hybrid and the self-consolidate hybrid. The yellow one is the ECC, and the other one is the hybrid and self-consolidate hybrid. In all three cases, you can see the ductility there. We did strain gauges. It's all explained in the poster. We did strain gauges along the rebar, and you see that along the whole rebar, you have strain hardening. There's no localization. There's no grabbing, what people are very afraid of. In summary, so the high-performance fiber-reinforced composite enhanced damage resistance, specifically when it's exposed to both environmental and seismic loading conditions. You extend the surface life of the concrete structures, and of course you make the structure more sustainable because you're preserving some of these, preserving some of the resources. It's a holistic approach, and I want to point that out. It's a holistic approach in regards to durability of concrete structures, because most of these structures are always exposed not only to one deterioration process. There are many deterioration processes that occur at the same time. Research needs. I think we covered the hybrid fiber reinforced without reinforcing bars, so we would know very well how they behave. What is still needed is that kind of synergy between the rebar and the matrix. Very few studies have been done, and we are very grateful to Pierre that there's had that foresight to really look into that. We were the first one really in the US looking specifically at that synergy between the rebar and the matrix. We used this one then, this is together with Sarah Billington, we used this to do model development and then go into design guidelines. And of course, what we also need is large-scale test verification of these materials, both for cast-in-place applications and accelerated bridge construction. I just want to point out, for some of you who might be interested, for tomorrow afternoon, we have much more presentation on the high performance for bridge structures as well as for tall buildings. If you're interested in the nuclear, you may be interested in some of the talks as well that talk about impact resistance. And then we merge the high performance, together with the life cycle analysis and sustainable material certification and so on. So we try to merge these two areas together. And with this, I would like to thank you for your attention.
Thank you, Claudia. There will be a very active session tomorrow to discuss this further, but are there any questions now? Yes.
Just a quick question. Have you done any work in terms of using high-performance concrete as retrofitting existing conventional concrete? And how does that kind of work?
Yeah, I personally have not, but there will be a talk tomorrow in the afternoon specifically for that. He uses also high-performance fiber-reinforced composite specifically for retrofitting of bridge structures. I personally have only dealt so far with new structures.
Another question, perhaps? If not, then be sure to come to the session tomorrow on high-performance materials. It's application to performance-based earthquake engineering. We have now a schedule for a break. But just as a reminder, we'll have the student poster session right after the next session, approximately 5 o'clock, and there'll be some refreshments and a no-host bar. And tomorrow we'll start again at 9 o'clock. There'll be breakfast and registration at 8. And then you don't have to come back to this room. There's not a plenary session, but we'll go directly to the breakout sessions in the morning. So look at the program for that if you're not able to stay until the closing of today's meeting. So let's take about 20 minutes for a break. Try and reconvene then in about 20 minutes, and we'll go through the last 3 presentations. Thank you.